Hello team, welcome to another video guide and walkthrough, this one for Programming Assignment 5, the interpreter. In the previous video guide for the interpreter checkpoint actually covered the majority of the pure interpreter material. We want to give hints on things like how to do dispatch or how to do new and initialization. So in this video guide we're going to cover a topic that depending on student background, can be almost as difficult as writing the interpreter itself, and that is managing complexity, especially with respect to testing and debugging. At some point very soon, this may have already happened, you'll have an interpreter that works on some test cases, hello world, maybe some more complicated ones, but does not agree with the reference on some others. So when you submit it for grading, you'll see a number of failed test cases. And the question is, what can you do about that? Now that we might have, 100 test cases, doing all of this manually can be a significant time sink. So in this video, we're going to cover automated testing, and I'm also going to walk you through a use of the Delta Debugging algorithm, for which a tool is already available. All right, let's get started. For the purposes of this video, I have brought along two student submissions. These are actual compilers written by students in previous years that were not quite perfect. So these are stand-ins for your compiler when it's not quite done. And one of the first things we'll want to do is figure out what they're currently getting wrong. So I'm going to start with all of the cool examples. And now I have a number of cool files. And I could run cool on each of these in turn. Maybe something like A to I. And then run a given student implementation and see if it matches. Oh, look, this doesn't quite match. It's supposed to be 6789, but this says 789876. That's close, but that's not the right answer. I could do this manually, but after I have a large number of test cases, that might get a bit tedious. So what I'm going to do is show a very simple regression testing, sort of automated testing test suite. And we'll pick one of these students, student 3 for now, and have this be the student of interest. I have multiple failing compilers, but you would only have one, right? So we'll have that be the student. So we'll make our shell script, and we're going to write it in bash. And this special thing at the beginning, the hashtag and then the bang and then bin bash, tells OS X or Cygwin or Unix that this is a bash shell script. This is important because there are other shells that don't have exactly the same syntax. And all of the examples I'm going to be giving use literal bash. All right. So what I would like to do is just conceptually iterate over all of the tests in the current directory and compare student exe's output to the reference interpreter's output. All right. Well, it turns out that there is particular syntax for iteration in bash, and it looks like this. For something in big list, do commands, done. All right. And this something is the name of a variable. We'd like to say test, but it turns out that's already taken, so we'll just say t. And then in big list, we might say, oh, I've got all of these CL files. And then over here, I could do something as simple as just echo. Right? So this shell script is going to iterate over all of the CL files and print out got here and then the name. Right? Just in case we need it, we will make it so that everyone has execute permission on our regression shell script, and then we'll run it. And it says we got here arith A to I cells hello world. All right. We could also use tabbing. This is the sort of standard tabbing for shell scripts in this regard, and this won't change the output anyway. All right. So we have all of these CL files, but actually for the purposes of the interpreter, we start with CLType files. So let's run them all now. And we'll take a cool and we'll ask it to type check each one. And before I run this, let's just take a look in the current directory and note that there's only one, the one I did manually. But now when I do regression, well, we've got CLType files coming out the wazoo. All right. So now what I want to do is for every one of these CLType files, right, I'm going to interpret it, and I want to store all of the output as something like output.reference. But I'm going to use this special greater than and then the ampersand in bash to mean that I want to redirect both standard output and also standard error. And this is just in case there's some sort of weird internal compiler error, usually with the student code. We want to make sure we capture all of that. And sometimes these test cases can come with test inputs. I'm going to be lazy and always read input from devnull. So after running the reference interpreter, I can also home, Weimer, desktop, PA5. I can run the student version. Cool was in my path, but maybe this directory isn't. Right. And I will also run it on the test case, and I will redirect it to the student output and read it in from devnull. Now, right now, every time I go around this loop, we'd overwrite output reference and output student. But I just want to debug this shell script as I'm sort of halfway through it. All right. Now, it just so happens, right, let's try this out. All right, we're going to see not a whole lot happen, and it will say done, but I can now see the output for the student and the output for the reference on A2I. And I notice already that they're potentially a little different. When I run cool on arith.cltype, well, potentially it goes on forever because arith.cltype is this sort of interactive program, right? You would add 56 and then you would quit. So even though we're getting a different answer on this, and it would be handy for debugging, because arith.cl expects interactive input, I'm going to remove it for now. We can always get it back later. And this sort of manual curation is something I also encourage you to do, especially if you've been doing the test-driven development portions of the exercises. You may have hundreds of test cases. You probably don't want to use all of them. Some of them are going to be too obnoxious or too long or subsumed by other tests. So let's get rid of arith. All right. But now, when we rerun this, all right, the first thing we did was A2I. When we run cool on A2I, it says this, and the reference output does not say what we're expecting because I no longer want the type. I just want to interpret it. The reference output says the right thing, and when I run the student on, and that's the same thing we see from here. So we've captured the input and the output. But now we want to check to see if they are exactly the same. So instead of echoing done, we're going to use a little conditional here. And loosely, if they are the same, then I want to echo or otherwise indicate that we passed this test. Otherwise, I want to indicate that we failed this test. So the question is just, how can I tell if they're the same? And for now, we'll use diff. And I could just compare the student output and the reference output. Now, every time there is any difference, diff would write it to standard output, which would mess up our little testing. So we're going to redirect everything to devnull. but Diff will still return an error code indicating whether they were the same or not, which lets us get this pass and fail. For now, I'm going to pass in these arguments to Diff that relate to how it handles blanks. In reality, blanks are important for programming assignment 5, but because I'm testing some student code that may not be perfectly platform independent, let us say, we're going to put this in for now, but this is something you'll want to revisit. Right? To do, think about whether we want BD or not. Right. And now let's see what happens with our regression testing. And we can see for this student that we fail a number of these tests, the first three, A2I, cells, and Harry Scary, and we pass a bunch of the rest. All right, that's pretty handy. So now let's see what would happen if we were playing the role of the other student. Let's say we were really student 5. I can run regression. Oh, and we see that student 5 is not doing quite as well. Student 5 is failing more test cases, although they both pass hello world, which is a good sign. Right? All right, but let's be student 3 for now. All right, fail, fail, pass, fail. All right, so let's just pick one of these, like Harry Scary, and say, oh, you know, we're not getting the right answer, so let's go investigate that. When we run cool on Harry Scary, oh my gosh, and when we run the student on Harry Scary, oh, I do not want to do this debugging. Look at how hideous this is. Very long numbers that are different and of different lengths, and this is not fun at all. So what I really want is something to help me out. And the basic problem with debugging is that Harry Scary is long-ish, right? And it's got all of this stuff, like case expressions, and here it's got static dispatch, and we don't actually know which parts are wrong, right? There's a lot of stuff going on here, like this almost inheritance cycle where we've got attribute initializers, we've got a bunch of cases, we've got a bunch of additions, we've got static dispatch, and getting even just one of these things wrong could be why we're getting all of the wrong output. Right? So it would be nice if we could shrink this test case down. Now, we've talked a bit in class about how to do that, right? In the limit, you would just, you know, sort of delete half the lines and rerun it. The problem is, if you delete half the lines in Harry Scary CL, it's not going to type check, right? Because all of the classes sort of refer to each other. So you'd have to be much smarter about it. You'd have to think very carefully and say, well, maybe I can remove this one line. Nope. You know, blah, blah, blah. And every time you considered removing a line, you'd have to compare the reference output against your output. And what you'd want to do is find the smallest version of this file where the student output and the reference output differ. All right. And it's going to turn out that we can do that automatically, right? Or we can get pretty close automatically. And you may recall that in one of the earlier lectures, you were encouraged to read a bit and watch some videos about Delta Debugging, an algorithm or a tool that does this for you. Right? Part of the Delta Debugging project by Andreas Zeller, which sort of automatically does this hypothesis testing until it finds the smallest region, the smallest bit of your code that still fails. And turns out that there are concrete implementations of Delta Debugging. One of them was written by Dan Wilkerson and Scott McPeak, and we're going to use that. So let's go get it. It's a tar GNU zip file, which is like an old version of zip or rar. So we can just extract from the zipped file. Right. And now if we relook, we see there's this directory in here, Delta. Right. And it's got its README, and we could definitely take a look. Probably most important for students is that in this www directory, there's a how to use Delta HTML file. And you can see that much like many of my web pages, this predates modern HTML standards, but you can go read about how to use it. We'll run make just in case. All right, this, looks questionable, but this is really just a warning. So we ended up compiling everything that was there, top form flat. We're not even going to use top form flat. The big deal here is delta, which is a Perl script that accepts a number of arguments. What a test is, where to put the minimal output, some sort of granularity. And the basic idea here for Delta debugging is we're going to write some test that says whether a file is interesting. And Delta debugging is going to try to find the smallest thing that is interesting. For us, interesting means the student interpreter and the reference interpreter disagree, because that means usually there's a bug in the student interpreter. So one of the things we might want to do is do some delta debugging. We want to minimize. All right. We'll make our own little subdirectory here just to keep things tidy. And in this minimize directory, we need to write a script that's going to indicate or return information about whether or not a candidate input, like a candidate cool file, is still interesting. So I'm going to call this testcool.sh. You'd love to call it test, but again, the name is already taken. All of my shell scripts start with bin bash, just because I want to make sure the syntax works correctly. And again, what's happening here is we are given a single cool file as our only argument. This script is as its only argument. The argument is called $1. This is just how shell scripting works. The first argument is $1. The second argument would be $2. We should return 0 if the argument is interesting. We say that a file is interesting if it is a valid cool file and the student and the reference disagree on the output. I want to check both of those. All right. So this script will be invoked many times in many separate directories, so we should be careful about temp files and path names. All right. So basically what's going to happen is if you have some input file like ABCD, this Delta debugging tool that we just downloaded is going to delete the first 2 lines and call this shell script on it. And if that's not interesting, delete these last 2 lines and call the shell script on it. Or what about the middle lines and call the shell script on it? It's going to exhaustively try a large number of those combinations for you, just bam, bam, bam in the background. All right, which is going to save us a lot of time. So this is one of those tooling things where we pay a cost now, like it takes 5 minutes to write this shell scripting, but then it's going to save us a huge amount of time because we could have this testing working while we're sleeping, right? Or while we're in class. This could run on, your home machine or whatnot. You just leave the room and it's totally fine. All right. So the first thing we're going to do is make sure to clean up any old files that may be lying around. There shouldn't be any, but just in case, I'm going to remove all the CLType files. And we'll even pass the -f argument to remove. -f means force, which means don't die if there's no such file. And also try hard to remove it if there is one. All right. We're going to be passed a cool file. All right. And I will just rename it. I'll take our argument and move it to hello.cl. Copy our argument to hello.cl. And 2 reasons for this. One is for readability. So it'll be easier to see what's going on in this script. Right? And the other is Delta may use a different suffix than CL and cool.exe depends on suffix strings. So now that we have this hello.cl, we're going to call the reference interpreter and try to type check it. Now it may be, if you have some file like class main, blah, 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 if you delete one of these lines, like if you delete this last line, this is no longer a valid file. So in this case, I don't actually care if the student and the reference disagree, because you would never get this input at this stage, right? The front end of the compiler would have ruled it out. So we only care about, like, if the type checking worked, then. Right? So how do we check to see if the type checking worked? Well, if the type checking worked, we have hello.CLType. So we'll just check for that. And it turns out that in Bash, you can check to see if a regular file exists with this bracket, square bracket notation, and then -f. This means test for this file, hello.CLType. We see if it's there. And this if-then phi is just a Bash syntax. Right. If it's there, I will run the reference interpreter on this file. And once again, no input for me. You will want to revisit this maybe and pass in some interesting input. And we will also run the student interpreter. Oh, that line break matters. Don't do that to me. All right. We'll also run the student interpreter and save this to output student. And the rest of this is going to look a lot like before. If there's a difference between the student output and the reference output, right? Well, if there's no difference, right, then this is not interesting. Right? So we have the same output is not interesting. Otherwise, different output, yes, interesting, right? This is helping us to minimize the bug. And if you made it all the way through here, and you didn't exit at one of these, this means it failed to type check. This is not interesting. Right? So here is my shell script, right, that is determining whether a given input cool file is interesting or not. And the input cool file that I'm going to start with is Harry Scary. Right? Because initially it was hard to figure out what was going on in it, and I'm hoping that Delta can help me out. To run Delta, I need to find the Delta executable, and it tells me I have to specify a few things. Right? So for me, the test script is this test cool. Oh, just in case, let's make sure everyone can execute this shell script. All right. So we are going to test using this shell script, and when we are finally done with this, right, we'll want to copy the output somewhere. Like we have a minimized harryscary.cl, and I want you to start with harryscary.cl. Now, Delta Debugging is going to do some sanity checking at the beginning, and we're going to see pretty quickly whether we've got our shell script correct or whether there's some sort of type error. As scary as this may look, this actually means everything is working correctly. You can ask Delta to be more quiet if you don't want to see all of this output or if you're going over a network. But these ranges, like 2 through 4, 6 through 8, right? These are basically the lines that are being deleted, or if you like, the lines that are being retained. It sort of doesn't really matter how they're printing it out. But this indicates that they're able to make forward progress. They're automatically minimizing this for you. So it says we copy the minimal run to minimal harryscary.cl. Right? And let's just take a look here. Oh, this got a lot smaller. Right? It started out as 1.2 kilobytes, and now it's just 400 bytes. Let's go look at minimal hairy scary.cl. Oh, we've removed a lot of things. Now this isn't, perfect. It's still more than 3 or 4 lines long, but it's much easier to just stare at it. Notably, all of the cases only have one branch, so we know the problem isn't with some, case reordering multi-branch issue. We don't have that static dispatch anymore, right? The out sign is totally gone. There's no addition. So we've removed a lot of things. Indeed, some of these classes are even totally empty. All right, well, Delta Debugging promised us that the student and the reference were going to get different outputs here. So let's just double check that. The reference says, oh, Stack Overflow. Very interesting. And the student says, ho ho, some sort of OCaml error. All right, so the student's program is crashing when it is supposed to very nicely indicate that there's a Stack Overflow on line 15. So this is now a much smaller program. And indeed, now we would sort of take over from the computer and try to figure out, where is this Stack Overflow on line 15? Was it line 15? Yeah, line 15. Well, we call new foo, but we see that foo inherits from Baz. So whenever we make a new foo, we're going to have to fill in this A, but also fill in this G. And evaluating the G is going to make a new foo. So we loop forever, right? This is a very interesting instance of looping forever because it's essentially an overflow in the initializer, right? It's as if we had class yada. This sort of thing would cause cool to loop forever because to make a yada, you have to make another yada, so it's yada, 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 right? It's just hidden here because it uses both foo and Baz, and they sort of refer to each other. All right. So we've minimized the test case to the point where a human can just sort of stare at it and understand it. All right. So that was actually pretty handy. That worked out fairly well. And we could go inside here in temp0, which was created by Delta, and you can look and see at all of the things that it tried along the way that were interesting. Now it has renamed them .c, but we wanted .cl, so this is just another program. And this arena directory is where we can see this hello.cl. Right? This is the place where it was running our little shell script. And I guess there's even a log that talks about which lines we're considering removing or that sort of thing and how long it took. All right. So we have minimized hairy scary to something smaller where there's a difference, and now it's going to be much easier for us to debug it. But we started out with sort of a different error, and now this ended up producing a program where the reference compiler indicates a runtime error. Now this is definitely something you have to do for PA5, but let's say we didn't want to do that, right? This is like we started off debugging error 1. All right, so if we have the student code and we type hairyscary.cl, when we run the student code on this, we weren't getting these weird exceptions or stack overflows. We were getting the wrong numbers, right? So what if we really wanted to use Delta to minimize this wrong numbers thing instead? What if I don't want to be getting this error? All right. Well, what if I'm just going to make another, we could do this all in the same directory, but I'm going to have different directories for the purposes of this video. What if we want to minimize with no errors? Right. So I'm going to remove temp0, and I'm just going to change, I'm going to remove all the minimized stuff. I'm going to change test cool, and we're going to change the oh my gosh, what's this E output? Doesn't matter. I'm going to change the definition of what it means to be interesting. In addition to all of this stuff we had before, right? We're going to check to see if error occurs in either the student output or the reference output. Let's say the reference output. Let's say we trust that a little bit more. Right. So runtime error not interesting. different output and no runtime error. Interesting. So here we've now sort of changed what this is doing, and reference cool has no runtime error on the input. This is just a choice we're making. We're saying for the purposes of debugging, I want to minimize this down to get the smallest thing I can where the student and the reference disagree, but there'd be no runtime error reported by the reference. Oh, and we'll want to redirect output to dev null, otherwise it'll spam the screen. Okay. So we'll just go back and find our previous. We could be faster about this, but why not? We'll rerun this command from before. I am the very model of a modern major general of information, animal and vegetable and mineral. No, wait, that's not the right order. Oh well. So this could take some amount of time, and actually that's handy, right? That's something that we potentially care about, because you could have this sort of thing run overnight, and then the computer is doing all of the work for you. Ah, great. So we're finally done. Now let's see what min-hs is. Oh, now, more things were retained, like the addition is still here, and the static dispatch is still here. But let's see what happens. Oh, this is a much smaller number. Well, that's good. And then we're going to run the student code on this. Oh, and we see that the student code is printing out 1111, whereas the reference prints out a 5 immediately. But this is much easier to get a handle on. Right? This is a smaller file that was produced for us automatically. And we saw that there was this issue where we made a new baz, and there's only one instance of outint. So it must be that this h, we were somehow getting h is 1. All right, that seems pretty reasonable. But when we run cool on this, cool prints out 5. So we can infer that cool must have done something like this addition here, right? 1 plus 1 is 2, 3, 4, 5, maybe, let's say. And we were not. Or it could have been that Do down here was doing some of this addition. But however this goes, right, we should have been printing out 5 and we were printing out 1. So this suggests that we weren't doing the initializers in the right order. We didn't call some of the functions, but now we know exactly where to to sort of start narrowing it down. Like we could add in some debugging printouts and re-minimize, or we could do it manually. All right, so we've been able to minimize these first student assignments, and now let's just do this one more time for a different student. Let's say that we're now student 5. Again, you're always only one person, but for the purposes of an interesting video, we're showing multiples of these. And we just want to rerun our regression testing, and we see that, we're failing a bunch of these. So, I don't know, let's take a look at list. Right. And back here in minimize, we're just going to copy list to the current directory. And cool type, and just run it. What does cool say on list? It says 5, 4, 3, 2, 1. For that, prints out this interesting triangle. And what does the student say? Oh, some sort of internal compiler error. All right. So let's see if we can go minimize that. And again, the theory here is that list itself is very big, right? This is like hundreds of lines. So let's get rid of some of this complexity and go find our line for doing Delta debugging. But this time we are minimizing, oh, no. This time we are minimizing list, starting from list. We're walking. We get to watch it doing some work. What's this scrolling output that says parse error and syntax error? That's the part where Delta debugging, which is not very smart at all, is deleting things that are important to cool, like semicolons, and then the result is not a valid cool file. I didn't redirect those to dev null. All right, so now we've got this minimal list, and our original list was 4K, and we've minimized it down to half a K, so we feel much better here. All right. We've got our class list, our class cons, our class main, and let's see what happens. All right. The reference interpreter immediately gives a dispatch on void on line 32, whereas the student, we'll have to whereas the student doesn't notice the dispatch on void. That's very brave. Well, now in this minimized version, we could go down to line 32. Oh, this is interesting. Any sort of dispatch on void here would have to be mylist.isNil. This would have to be that mylist is actually void, and I'm not surprised because mylist is void sort of immediately. So this should be very easy for us to trace through if we're the student, right? Because this is just a variable that starts out void, nothing happens, and then sort of immediately on line 1, we don't notice that it's void and we dispatch something on it. Right? So even though there is all of this stuff about cons and list, with a combination of Delta debugging and us just eyeballing it for 30 seconds, we kind of get to the heart of the matter. But once again, we changed this, we started out debugging one instance, and then we found something where cool would give this exception. What happens if we want to not look for errors like that? So once again, we could run Delta debugging. Now, things to mention. You could end up producing a program that would cause either the reference interpreter or your cool program to run for a long time, like calculating the digits of pi, or even loop forever. So in your test shell script, you probably want to add some sort of timeout. If you're on Linux, you might use ulimit to do something like that. Limit the running to 1 second. All right, we'll let this go for a bit. And it has produced minimal list. Right. Oh, and we see that this one is a little different. We've got this list that's 1, 2, 3, 4, 5 at the start. And let's see what cool says. It produces no output. Probably, if I had to guess, the way for it to produce no output is that print list never actually prints out the contents of the list. If L is nil, then we output the string. Otherwise, we call print list on L.tail. Yeah, so this only prints out a new line at the end of the day. It never actually seems to print out the contents. But what does the student answer say here? We're going to type check. And now we're going to run the student. Right, and this is the original problem we started with, right? The student's code has some sort of internal OCaml exception, and now we have a much smaller cool file, right, that really isn't supposed to print anything out, that's going to help us find that. So, again, this video was about managing complexity. You're probably going to end up with a large number of test cases, and you may want to be able to automatically check which ones you're passing and failing without having to submit it to our grading servers. You're only supposed to do that at most once a minute. They can be slow, right? So we showed how to do that at the shell script, or with the shell script. And then we also introduced this Delta debugging tool, where all we had to do was write a script that determines if an input is interesting, and it minimized the input to be a smallest interesting input that it could find. And sometimes we put in some conditionals there, like, oh, I only want to find ones where the reference compiler wouldn't raise a runtime exception. And that seemed to work out fairly well. Now, there's no real substitute for you paying careful attention to test cases and looking through your own code. Once you've handled things like dynamic dispatch and new, then the next big steps are things like case or other system calls. But hopefully this sort of automated approach can mean that even though this is a big project with a lot of test cases, it won't take you as long as it would otherwise. Good luck.